Alright, welcome back, class. Now, on problem number 62, a squirrel is shot out of a cannon at a velocity of 343 meters per second at an angle theta equals 90 degrees above the ground. Calculate what type of cheese the moon is made out of. Neglect air resistance. Now, there's a problem with this question. Can any of you students tell me what it is?
Ooh, I know. Ooh.
Yes, generic student name.
It says neglect air resistance.
Very good, generic student name. We do not neglect air resistance in this class. That'd just be silly. Hi guys, so since summer's officially started for most of us, I figure I might as well start making some more videos, because I know all of you love learning about math and physics in your spare time. So first things first, I'd like to note that I took most of this information and learned pretty much all of the information from John R. Taylor's Classical Mechanics. If you're into physics and want to start learning classical mechanics, it's a very good book for it. So as you can see, this little mechanic guy working on a classical car. So it's like a classical mechanic, kind of like the classical mechanics. Get it? Okay, we're done with that. So what we're going to be talking about in this video is air resistance, and a lot of first year physics problems do ask you to neglect air resistance because it does get a little bit complicated. In this video we'll talk about how air resistance is precisely defined, as well as what equations stem from it, and how you can use it to approximate a lot of different cases. Not every case, but a lot of cases. And it does get a little bit complicated, but we'll work through that. And the reason we want to approximate is if we do find exact values, it will be rather unharmful, but it'll get really complicated for pretty much every single case that's realistic and applicable to real life. So we're just going to focus on approximations right now, and we're going to be happy with that. And these approximations will be good for about 2 to 3 decimal places, which is about all you'll ever need in classical mechanics. Okay, so now time to actually get on to air resistance. So first off, the force that air resistance causes and is related to is called the drag force, and it's usually written F drag. But for the sake of these videos, we're just going to write F, because it's the only force that we're going to be dealing with besides gravity, and that's usually written mg, so we'll be good there. So the drag force comes from an object going through a medium and colliding with particles as it does that. So if you take a ball, for example, and throw it through air, it's going to collide with air molecules like CO2, argon, nitrogen, oxygen, things like that. But if you throw it through water, you're still going to have a drag force, but there are going to be a lot more particles, because water's clearly denser than air, and there are going to be more particles exerting a force back onto the ball, so it's going to have a greater drag force. It's going to slow down faster. It's not air resistance, but it's the drag force. And if you were in a vacuum or something like that, or space, there would be no drag force because there are no particles. So essentially, the drag force is a very direct consequence of Newton's third law, which states that for every action force, there is a reaction force of the same magnitude in the opposite direction. So given this knowledge, we can figure out what direction that the drag force will always be in. So we first look at what types of forces is the ball itself exerting on particles. We're going to assume that we're using a spherical ball because it's the most basic shape to use, and it serves for pretty much every example that we're going to use. So suppose we have a spherical ball. It's hitting these air particles. And of course, there are going to be a lot more than 5, but we're going to use this as a drawing. So it's going to force this one to go in that direction, this one to go in that direction, always go tangent to the circle, or sphere. And remember, this is in 3 dimensions, so there are also particles going like this and like this and like that in all sorts of directions. So the important thing to see here is that when these forces happen, say with magnitude k, there, force with magnitude k, these are all magnitude k, we're going to have a force in the opposite direction, the reaction force. Also a magnitude k. So, what does this mean? So, if we're looking for the direction that it's going in, we can sort of see from this collection of vectors that if you sum them all together, then they're going to have a net direction of this way in the opposite direction of where the ball's going. Because, for example, if you had a air particle right on the top, then you'd have a vector going about right, or not right on the top, if you have it just past the right on the top, you're going to have a reaction force coming back like this. But if you have one just past the bottom, like right here, reaction force will go like that. And if you add the vectors, the direction is going to cancel out into just being a small vector in that direction. That's going to work for every possible position. If you have these, they're going to cancel out. If you have ones like that on either side, going into the board and out of the board, they're going to cancel out. Everything's going to cancel out. So when you integrate or sum up all of these forces coming from each individual particle, we're going to see that the force is going to go in the opposite direction of the velocity. Another important thing to note is that it's okay to assume that particles are evenly distributed, since there are so many billions of particles. If one of them is not canceled out, then it's not going to make a difference. We're going to assume that this sums the way I've described and the force is in the opposite direction. It's a best approximation. Alright, so now that we have that established, we can erase this and move on to just the equations. Alright, so to derive these equations, we're going to start with a particle or a ball or whatever you want to call it of mass m moving with velocity v in the direction of this vector. And I've drawn it as a dotted vector because that shows that it's not a force vector, because generally you draw solid lines to represent force, and this is not a force. So, what forces will there be? Well, we have weight, of course, and we're going to assume we live on Earth, which is safe to say. Weight is equal to the mass times gravitational acceleration. Okay, we have one force. What other forces are there? We have the drag force, of course, because remember, we do not neglect air resistance. And we call that F. So, how do we write this equation? So if we want to first start by finding the function that gives us the drag force. And the drag force will always be dependent on the velocity, both the direction and the magnitude, because the velocity of the mass will determine how much force it is exerting on each of the individual particles it's hitting. And that will in turn determine the amount of force that is exerted back on the ball in the opposite direction. So, suppose F vector, by the way, is equal to F of V, and it has to be in the direction of V, but it's negative. So there's our formula for the drag force. Yeah. And remember, to find this unit vector in a certain direction, we do unit vector is equal to the vector itself over the magnitude of the vector. So whatever this turns out to be, there you go. So we have this as our formula for friction, not air resistance. Okay, so we're going to make a bit of a jump here, but we're going to come back into it in a minute, so you just got to trust me. F of V is going to be equal to B times the magnitude of v plus c times the magnitude of v squared. So this is our equation, and remember, you gotta trust me, we're gonna come back and talk about it in a minute, but first we're gonna find the equation for the position at a given time based on this weight and F drag force. Okay, so I went and cleaned this up. So what we first want to find, we want to split this into components. So we can find, well, first we're going to have to do a little bit of calculus here. We want to find the forces in the y direction and the forces in the x direction. So if we start with net force in the y direction, what do we have? Let's assume for now that that's positive and that's positive. Okay, so down is positive and right is positive. So that means that one force we're going to have is the weight. And since that's in a positive direction, we just write mg. And we also need to split this up into components, right? So this is where it gets a little bit annoying. Do some vector stuff. We need to split this up into components, and to do that, we're actually going to, I'll be right back, I'm going to draw this somewhere else. Alright, so we split it up into components down here. Now we just need to find theta in terms of v or f or something. So we can see that, actually we need to find it in terms of v because that's our one given. Suppose this is a unit vector I, since that's the unit vector commonly used in the x. You know what, we'll just use x. Unit vector used in the positive x direction. And remember, this is positive. So there we go. So we can find this angle, which is the same as this angle. It's pretty obvious. By using the formula. Let's see. V dot x over magnitude of v times the magnitude of x. Cosine inverse of that. So it's kind of annoying to write. So we'll just write this down here and say theta is equal to this. Okay, I got rid of the magnitude of x because since the unit vector, it's always just 1. That's obvious. So we'll come back to this. We have mg plus, now we have our y value of drag force. I don't know why I always forget drag force, but it's drag force and it's air resistance and it's drag force. Okay, so y value of drag force plus F sine theta. There we go. And if we have, and this, if this ends up being a negative value, if this velocity ends up being below the positive x unit vector, then we'll just get a negative theta, and that'll end up being negative, so it'll all be fine. But notice when we come to f of x, the only force will be the x component of the drag force. That'll always be in the negative direction because we're assuming that the object is always moving in the positive direction. If not, we could just flip our coordinate system, so it'd be the same sort of deal. And notice, since it's cosine, then the sine of theta will not affect the sine of the component, so it's all fine. So it's negative f cosine theta. So there we go. These are our two components. And this is a little bit elementary, first year physics stuff, and so we're just going to move on. This isn't really useful in the next few videos, but it's good to get an idea of this whole system. And so now that we've gotten that out of the way, you kind of have an idea of what's going on, all the forces, we're going to move on to this. Okay, now back to this. If we notice, we have two main terms here. So they each have very important roles and they're very different. So for simplicity, we're going to call them F linear and F quadratic, obviously after the degree of their exponent. So now we need to investigate what exactly these are. And first we're going to look at B and C. So these constants, B for example, is defined as this constant beta times d, which is the diameter of whatever object we're using. And remember, we're going to stick with spheres, so it's pretty easy to think of a diameter of a sphere. And the reason this works is because air resistance is dependent on the size of the particle or ball, because that determines how many air particles it impacts. So this constant is experimentally derived based on that, because it'd be really, 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 really complicated to try to actually figure out mathematically. We're not going to even worry about that. And then C, which is the quadratic constant, is similar, but it has d squared, which sort of makes sense why it goes with v squared. And gamma is another constant, 0.25 instead of 1.6 times 10 to the 4th. So it's a little bit bigger, but notice that the units are only there pretty much to make sure that f of v ends up in newtons, because, for example, beta times diameter, the meters are going to cancel out because diameter and any length is always measured in meters in physics. So we're going to have newtons times seconds over meters. And then you multiply b times velocity, which is meters per second. So you're going to cancel out and get newtons. The same thing works with this equation and with c. So it'll give a little more, so to give a little bit more background to these two terms, they're actually quite different and they serve their own purposes. So the f linear term is derived from the relationship between the object and whatever medium it's flowing through is viscosity. So this is derived based on viscosity, and this is directly related to the diameter of your object. Whereas the f quad term is related directly to density of the medium or fluid it's going through, and it's also related to the cross-sectional area of the object. So again, we get this constant when that's experimentally determined. But we won't really go much into that, specifically why that exists, but we're going to look at different cases for which, say, f quad can be negligible and things like that. So a very easy way to figure out what may be negligible and what may not be in a given situation based on a velocity or a diameter, the two givens that we have, we can find a ratio between f quad, I can't write, okay, f quad over f linear. And if we plug all these things in, I'm going to do that real quick, and then we'll look at what happens. So when we do the math, we end up with the diameter times the magnitude of the velocity times this constant, which is equal to gamma over beta. So in specific cases, we can plug in a diameter and a velocity and determine based on that which terms may or may not be negligible, and that'll make everything a lot simpler. Okay, so the first example we're going to look at to see exactly what this applies for and where f quad's good and where f linear is good is generic baseball. So suppose it has a diameter of 7 centimeters, which is about that, and a velocity of 5 meters per second. So if we plug it into this equation, we first need to convert this to meters, because we always have to have the right units, otherwise we're going to mess stuff up and get everything wrong. That would be unfortunate. So multiply by 1 meter over 10 squared centimeters equals 0.07 meters. So there's the actual diameter in meters. So if we plug it into this, technical difficulties. We have our constant, 1.6 times 10 to the third meters per second squared times 0.07 meters times 5 meters per second. So if we actually calculate that, we get 560 meters cubed per seconds cubed. And the units don't really matter since we're just looking at a ratio and they just happen to have different units, so this is going to happen. But what does this mean? This means that f quad is 560 times larger than f linear, which means that f linear is probably going to be negligible because it's going to barely change the amount of force. And since removing that and making it negligible will make the math incredibly easier, we're going to assume that that is negligible. So Fn is negligible. There we go. Now let's look at another case to see what else we can find out. So I went ahead and did 2 more examples since doing the plugging in arithmetic isn't really that important. For a raindrop of diameter 1 millimeter, so about that big, moving at 0.6 meters per second, F quad and F lin are pretty close to the same, 0.96. So you can't really neglect either of them, and that's kind of unfortunate, but it's how you're going to have to do the math. But if we have something really small, like an oil droplet, the kind of thing that's used in Millikan's oil experiment, if you're familiar with that, or the size of droplets that come out of perfume bottles and things like that, diameter 1.5 micrometers, which is pretty small, it's about that big, and 5 times 10 to the negative 5th meter per second, which is pretty slow, then we find that F linear is actually a lot larger than F quad, which means that F quad is negligible. So for sort of our 3 different cases where linear is negligible, quad is negligible, and neither are negligible, we can see that bigger cases, faster cases work for F quad, smaller, really small cases work for F linear, and about in the middle, which makes sense, neither of them are negligible because they're about even. So that's it for this video. In the next video, I'm going to go over specifically how to work with F linear, since it's the simplest math to do. Then we're going to work our way up to F quad and even putting them together. And your homework for this class is to, of course, like, comment, subscribe, and turn on notifications by hitting the bell button, of course, as every YouTuber wants you to do. So work on that, and then you'll be ready to do some serious math next time. Also, you can do any other stereotypical YouTube stuff that you want.